Hi, everybody. Thank you for tuning to this video. My name is Valentin, and today I'm going to showcase you the result of a little numerical modeling exercise that we conducted with these lovely people here, Elizabeth Steele, Ryan Mulligan, Daniel Collins, and Matthias Green. And we think that this method we developed is quick and robust for testing the propagation of tides in any paleo seas, actually. And I will try to show you how and why. I'm also going to turn off the camera so you can actually see the whole screen while I talk, but I'm still there. Also, you can access these results in a preprint on Earth Archive using this QR code right here. Yes, so rationale. For the people who know me, I've been working on this Upper Jurassic shallow marine unit called the Curtis Formation that crops out today in East Central Utah. And this is how the rocks look in the field. This formation can be subdivided in 3 subunits. So you have the log here on the left, and it's color coded. You can see this lower unit here in black is very heterolytic, very thinly bedded. The beds are quite tabular. And then when we reach this the surface here, we have a dramatic fascist change. We lose all the beds, we lose all the fines, and we're left with mostly amalgamated, very fine to fine grain cross-stratified sandstone. And as we go up section, you can see that the beds gradually come back in, and so do the fines, and then we slowly go into the supratidal deposits of the Somerville Formation. And when we look at these rocks, we do see quite a few evidences of tidal processes being active at the time of deposition. We have evidence of bidirectionality acting at different scale. You have the bar scale here, and you see how the bars are color-coded, this little rose diagram. The black line is the orientation of the photo. You also see bidirectionality at the dune scale, at the ripple scale here as well. We have I would say traditional tidal rhythmite here truncated, but this beautiful channel migrating. You can see the lateral migration surfaces here. And we have beautiful reactivation surfaces on subtidal dunes here. We also have evidence of waxing and waning of the flow, such as in these subtidal bundles. Here, we can also see it here at the dune scale. We also see these waxing and waning of the flow in this flazer to wavy to flazer bedding in these tidal rhythmite. I won't go into the detail of the fascia description. All of this is available in a few papers published in the past 3 years now. And there are some other papers as well that will discuss some other aspect of tidal process in the area. And lastly, also slightly younger strata that are still linked to the same epicontinental sea. They were interpreted to show also evidence of tidal processes. You can see this whole paper by Holland and Wright from 2020. So we have the field observation, and now this is the paleogeography of the Oxfordian for the area. You can see where we are. These are maps from Blakey, by the way. You can see where we are. We have the sun and sea connected to the Pacific Ocean by this narrow corridor here. Well, narrow is like 250 kilometers. And then we have the Curtis Sea flooding what is today Utah, and it's neighbored by the arid desert of Entrada. And so the question was, well, given this paleogeography, could tides actually propagate that far into this shallow sea? So this is why we did this numerical modeling exercise. So we took this map from Blakey, and then we extracted 9 different paleophysiographies. And so what we did is we attributed for each pixel a depth value, according to their color. So the lightest color, usually by the shoreline, will always be 0. So the lightest color is always 0, it's always at the shoreline. And then we varied the deepest, darkest color, and we gave it the maximum depth. And we varied that maximum depth to generate 9 different paleophysiographies. And we did this using this code that Elizabeth and I developed. which is available with the paper. We then forced these paleophysiographies in software called Dev3D, and we forced it with an M2 tidal constituent, and we simulated the tidal amplitude, the speed, and the bottom shear stress. We only simulated the M2 tidal constituent because we didn't want to make too many assumptions on what other constituent would be present. So this is an oversimplification of reality, yes, but it allows us to really test the sensitivity of the model. And now that we've, with the result we have, we can refine and add different constituent to it. But as a starting point, this is why we only simulated the M2 tidal constituent. We tested in the sensitivity of the model by varying the initial tidal forcing, so that we have a realistic initial tidal forcing at the mouth of the system up here of 0.5 meters. And then we had an extreme one of 2 meters, just again, test sensitivity of the model. And what we also changed was the value of the bottom drag coefficients. We didn't change the coastal geometry, although they it does have a big impact on the tidal propagation. But again, this is a map we have. We didn't want to make other assumptions on how would the shoreline look by changing the depth or the sea level. And these are the results. So we have a continuous results of the tides throughout the grid. And this is, a little GIF to show a 12-hour cycle of how tides propagate in the system. It's with a 0.5 meter initial tidal forcing at the mouth. You can see tides propagate into the corridor, and then you have in this area development of an amphidromic point. And then in the courtesy, you can see tides going down and coming in, and then coming out, and then coming in, with amplitude of up to 1.3 meters. At the time, you can see here also in this graph, the dashed blue lines here is the initial tidal forcing. So, 0.5 meter tidal amplitude. And you can see how amplified some of these areas, like down here or on this side of the sun, see how amplified they are. And so these are 3 tables showing the tidal amplitude versus depth. And you can, for maximum flow speed and maximum bed shear stress here. So on the vertical axis, you always have, on the left, you have the depth of the Curtis Sea, so depth here. And then on the right, you have the depth at the mouth of the system. So all the different physiographies we have, basically, maximum depth right there. So you can see that we tested from a very, very shallow mouth of the system from 300 to a quite deep 1,430. And what you can see is 3 things. The first is that certain paleophysiography configuration would lead to an overall amplification of the tides in the whole basin, up to 2.2 times the initial tidal forcing. The initial tidal forcing is is always 0.5 meter for all our simulation. And then we can see that some paleophysiography configuration would lead to an overall dampening of the tides in the system. And you can see the same, same with the speed and maximum bed shear stress. The second thing you see is that you have additional tidal harmonics that appear at certain places, but are absent from others. So you have a differentiation of the tidal amplification throughout the basin. It's something which is very well known from the modern system, but quite poorly documented in a rock record. There are 2 papers by Longitano et al. Look, I think it was Domenico Chiarella as well in it, 2012 and maybe 2016, that talk about the importance of physiography and relief of the seafloor on tidal propagation. So you can also want to check these papers out. And the last thing is we can, although not perfect, we can use the maximum bed shear stress values as indication of what type of sediment can be transported. And the higher the simulated bed shear stress, the coarser the transported sediment can be. And these these are two of the same maps. It's just the scale bar changing to highlight what's happening in this bottleneck right here. The green dots are control points, so are sedimentary logs. And what you can see is you have in this bottleneck quite coarse material, and then we have a fining towards the sun and sea, but also towards the innermost part of the basin. So the first conclusion really is that change in paleophysiography configuration dictates both the location and the amount of tidal amplification in the basin. If we compare it now to the field data, again, this is a map of the four corners. This is where we are around the San Rafael swell, and this is where the equivalent of the in the physiography. And so this is a map of the innermost part of the Curtis Sea. You can see here the maximum extent right there projected on the modern day geography. And you can also see here the rose diagram that shows the bidirectionality measured in the Curtis Formation. And here, this map shows the maximum bed shear stress, again, with these sediment classes, showing a coarser or higher energy here, so coarse sediment, and then we have a fining towards the end of the basin. And here you have a fence diagram of some of the measured sections we have, and we're going to focus first here on these ones with the red label up here on top. So it's basically the one here. And what you can see in the model predicts, quite high energy here, and then we go probably lower energy, so more mud, and then we have an increase in energy again, so probably more sand right there. And so when you look at the logs, we see from the north, so the logs I should explain also, green is mud and gray and gold is, so gray is sand and gold is gravel. So you can see that as we go to the south, we have an increase in mud content, and if we keep going to the south, the sand comes back in. It's not a perfect match, but the trend fits quite well. And if you look now on this part of the fence diagram, which is this bit, the model suggests also going from a higher energy to a lower energy. So we can see here very sand dominated, and then as we go further south, you can see an increase in mud content. Again, it's not perfect, but the trends are there. So we can say that our model is validated by field data, and answer our first question: yes, tide can propagate that far into the shallow epicontinental sea. And that specific maximum bed shear stress map fits very well with a paleo geography that has a 600 meters depth at the mouth of the system. The others don't fit really well. But the model is not perfect for two reasons. The first one is the model explained relatively well the distribution of the facies within the lower Curtis only. It fails to explain the very homogeneous distribution of sediment in this middle Curtis right here. So there is something that happened in the basin which we haven't figured out as we go from this lower unit to this middle unit right here, in terms of energy distribution. And the second thing that the model doesn't explain is the high sand content that is present in the southernmost bit of the basin. The model says it should be very, basically just mud, and the rock shows that it's actually quite sand rich. And one explanation to this is this shallow marine sea is neighbored by aeolian systems. So one way this sediment could be, could be so sand rich is if wind basically transports sand directly into the sea, and then the sea slightly modulates these deposits, or is as the sea was dynamic and you had periods of transgression and regression, and if we have a period of regression, then that would be accompanied by a development of the aeolian system. And then this aeolian system could then be subsequently flooded during the following transgression. So you basically, and then the marine current could then rework this sand that was there. So this is one explanation. Now I want to have a bit more maybe of a conceptual discussion about, impact on sequence stratigraphy. And so let's have this very simplified stratigraphy here with a bigrading trend, coarsening up, then fining up. And that basically reflects an energy level that first increases and then decreases. And that could be, basal maximum bed shear stress, the speed, or the tidal amplitude. It could be, increase of these values and then decrease. And this is, from our result here, we have the vertical line is always the same initial tidal forcing, and this is the resulting tidal amplitude given certain physiographies. So the question now is, can we find different relative sea level curves that could generate this exact energy pattern? And what you can see, if we have a constant relative sea level rise, so we will go from, we will enter this optimal tidal amplification window, and then we'll exit it. So we have an increase and then decrease in energy. That could be one explanation. Or we could have actually the relative sea level fall, same thing, like I keep shallowing up, and then suddenly I enter this optimal tidal amplification window, and then I exit it again, and that could generate the same curve. Or I can have a fold and rise, or a rise and fall, same thing. I enter and exit this optimal tidal amplification window. And then if we add sediment supply to this story, that's, it's yet another possibility. If I have a constant relative sea level rise, for example, but I have a sediment supply that first diminishes and then increase again, I will basically increase my water depth, meaning I can increase my, I can enter again this tidal amplification window and then exit it. I can exit it either by, slowing the pace of relative sea level rise, but still, it's still rising. Or, if I have a dramatic increase in sediment supply, I can also lower it and have basically relative sea level fall. So the stratigraphy is non-unique because it could have been the product of 4 or 5 complete different relative sea level curves. And this is for one spot in the basin. But now if we add other part of the basin as well, it further complicates the story. Because that curve, that red curve, was for one area, but we showed before that additional harmonics can appear in other places. Meaning that, I could basically have, with the exact same relative sea level curve, I would have 2 bigrading packages, whereas in the other place I had only 1. So how do you correlate these? If we have when we have a non-unique relative sea level, which can develop complete different stratigraphy, and this is, where is my flooding surface? Where do you put your how do you correlate these 2 parts of the basin, even though they underwent the exact same relative sea level history? So, is it time maybe to integrate this internal tidal dynamic variation to our classic sequence stratigraphic models? So I will stop there. To conclude, we've shown that change in paleophysiography configuration dictates where and how much amplification there is in the system. We also shown that the internal dynamics of tides are extremely sensitive to this change of relative sea level, and they can change a lot between different places in the basin, meaning that you have a non-uniqueness of the stratigraphy and the relative sea level change. And I would like to open a discussion with you guys again with this question: does it still make sense to apply classical sequence stratical concept to tide dominated basin, which don't consider the sensitivity of tides with respect to change in paleophysiography configuration? And I want to thank my co-authors who helped me a lot here: Professor Elizabeth Steele, Professor Ryan Mulligan, Professor Matthias Green, and Dr. Dan Collins. Again, don't hesitate to download the paper. And if you have any question or comment, please contact me, Twitter, email, whatever. So, and with this being said, I thank you very much for listening to me, and I guess I will see you soon.